6, binary exponentiation and heap sort. 2 topics. Part A, we do the first topic. Then we will use part B and C to do the second topic. All right, so part A, binary exponentiation. This problem, this topic is related to our optional project number 2. But this algorithm itself is very useful. So we should learn it. Then we can extend it a little bit to matrix multiplication. Then we can solve the, that Fibonacci, logarithmic Fibonacci problem for the general case in our project number 2. All right, so let me start. 8.1, Introduction to Binary Exponentiation. First, let me give you the problem. So our problem, number 15, binary exponentiation. Given a real number a and a positive integer n, how to find a to the nth power efficiently? That's simple. Okay? Here we know efficient means try to use the minimum number of multiplications. Try to use minimum or close to minimum. Yes, because later we will see if we really want to find the minimum, very complicated. And actually, if we really find the minimum, it is an open problem. To my knowledge, it is an open problem. Nobody knows that solution currently. But we have some close to optimal solution. Pretty close. All right, so now let's look at the solution idea. First, we have a experience. We use repeated squaring. We can greatly reduce the number of multiplications when we evaluate a to the nth power. Because when we use square operation, so every time when we just apply the square operation, we treat it as a special operation, we double the exponent. A to the n, so we do square, we double the exponent. So you can see double, every time we double, so we can quickly increase the exponent number, quickly. But another closely related technique, repeated cubing. Yes, in module 1, I give you examples using these 2 techniques. Okay, and we know for some of the special examples, repeated cubing can do a little better, slightly better than repeated squaring. All right, so here, same thing, using the cube operation. So every time we can triple the exponent. So we can increase the exponent number faster. Okay, faster. But to get a cube, we need 2 multiplications, right? To get a square, just 1 multiplication. So that's also a little more cost for the cube operation. So anyway, so here, based on our experience before, so we know if we do this double exponent way, we get a binary expression, because every time double, 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 right? Then you accumulate. The way you double the numbers, putting together, so that pretty much related to binary expression. We use 2 as the base to represent the number. So that's the binary expression. Similarly, if we do triple, every time triple here, triple there, right? And put things together, we will reach some expression, ternary expression, base 3 expression, ternary expression. Okay, yeah. So these 2 different ways. Yeah. But here for this part A, we only do binary expression. Although by analogy, we can generalize our method to ternary based method easily. Yeah, but to save time, we do not do it. Okay. All right. Now let's look at simple example. So we used it before. Yeah. When we calculate x to the 9th power, here 9 is not power of 2. Yeah. So we want to go to the general exponent number. Yeah. Here 9, not a power of 2. Yeah. So the number of multiplications, if we use repeated squaring, okay, the first one x squared, second one another square, third one third time square, then last multiplication. So 4 multiplications we can find x to the 9th. Yeah. All right. Then if we move to our project number 2, yes, optional, although it's optional, but here I like to connect this method to that project. Okay. For those students who want to try to earn 3% extra credit, okay, try it. Okay. It should be pretty interesting. Yeah. Non-trivial, you need to pay some effort. Yeah. But if you understand the algorithm here, not too much harder. Yeah. Just pay reasonable amount of effort. You can get it. Yeah. I still plan to write a code myself. Yeah. After I complete these videos, I will write a code myself. Then I show you my demo. Okay? Yeah. Hope you do the same way. Yeah. All right. Extension by analogy. Given a square matrix A, capital A, here we move to our project 2. We need to apply it on square matrix A. Square, not rectangular. So rectangular, then it won't work for this situation. Okay, square. More specifically, for our Fibonacci numbers, we only apply it on 2 by 2 matrices. 2 by 2 matrices. Okay, yeah. And a positive integer n, how to calculate capital A to the nth efficiently. Yeah, pretty close, right? Yeah. But here we just use the matrix multiplication. Okay, from project 1, you already have the, foundation part for the matrix computation. You have that. Yeah. Okay. Yeah. You can do any multiplication you want using your foundation part. Then, binary exponentiation, you need to understand it. Okay? Completely understand it. Then you apply it on matrix multiplications. You get a solution. Yeah. All right. So let's go to the next step. Yeah. Here we want our goal. We will go to the matrix way. Okay, if you want to work on the project too. Yeah. All right. So let's get back to our original binary exponentiation question. Yeah. All right. Here, we want to get to the binary expansion of the component number n. Our problem size n. We want to look at its binary representation or expansion or expression. Okay? Yeah. All right, so if we use the bits, binary bits, to represent a number, base 2, binary representation, so we can convert that easily, right? You can either call some special function or you just do some base 2 division. Yeah, also very easy. Okay, so you get all these bits. Okay. But we know the highest bit cannot be 0. Okay, yeah. So with that, we can write a base 2 expression in the standard way. Yeah. All right. So here you can see, can you closely look at this form and what special form can you relate it to? What special form you can relate this expression to? Okay, yeah. So you can see you can relate it to a polynomial, a general polynomial, p of x. Why? Here I want to connect to something that we did some work before. Why I want to do that? Yeah. Because you can see there is some very smart method that can evaluate this polynomial very efficient. We know that. In module 1, we compare this Horner's rule, extremely efficient. So here, because this form has some relation, pretty interesting relation to this form. Okay, or actually, if we plug in x just make x equals 2, base 2, then we get the number n, p of 2. Polynomial at the base value 2, we get n. See? Yeah, that's the key relationship. Key relationship. So this key observation can help us get an efficient algorithm with the help of Horner's rule. With the help of Horner's rule. Okay? But how to get that goal, how to get that? Still, a lot of work. We need to do a lot of work to get that result. Okay? All right. To finish this video, let me make conclusion here. To finish our first introduction video. The conclusion. Horner's rule can help us reduce the number of multiplications when we evaluate a polynomial. That's our experience. Yeah. But the polynomial connected to our binary expansion. Binary expansion. Okay, so we change our view here. All right, so by our experience, yeah, okay, so we can represent a positive integer in the form of a polynomial, p of 2. Now, at a special value 2. We're only interested some polynomial at a special value 2. Okay, yeah, much simpler. Yeah. All right. The remaining several videos. We have several videos. We will do this. Develop a Horner's rule-based algorithm to calculate monomial. Okay? So here you can see not polynomial. Polynomial multiple terms. But here we only do one term. One term, this a to the n. It is also, actually, we can call it a special monomial. Okay? One term. Monomial, one term. Okay? Actually, the general monomial form is like this. C, there is a constant coefficient, c times a to the n. Okay? So this is the general monomial. But our c here in our special case is just 1. Yeah. So here we want to calculate a monomial, not a polynomial, monomial. Yeah. But the exponent number will be represented in this special polynomial form. Okay. All right, so this is the introduction part. Yeah. Hope you get some background, basic understanding, so that we can, keep going to get this whole problem solved. All right, so let me finish